Stable and unstable systems. What do you mean by stability? Stability is said to be a very important system property. A system is said to be stable if and only if every bounded input results in bounded output. This is also called as bounded input, bounded output stability. To understand stability is very important to understand bounded signals. What is the meaning of the word bounded? So let us understand the meaning of the word bounded. Bounded input, bounded output. So bounded input is mathematically represented as a signal having finite magnitude. Right? So B is some magnitude. So we are saying that the signal xt has a finite magnitude for all instants of time. And if this is true, then we call the signal to be a bounded input. So signal xt is said to be bounded if its magnitude does not tend to infinity with time. Right? The magnitude of the signal. Try to understand the magnitude of the signal should be finite. Even if time tends to infinity, the magnitude of the signal should not tend to infinity. If this is true, then such a signal is said to be a bounded signal. Now let us try to look at some examples of bounded signal. Right? So the best and the simplest example is a unit step signal. Right? We know what is a basic unit step signal. Unit step signal has a magnitude 1 for all the time instants. Even if time tends to infinity, the magnitude of the signal is always 1. That is, the magnitude of the signal is finite even if time tends to infinity. And therefore, unit step signal is the best example of bounded signal. You can call unit step signal as a bounded signal because its magnitude is always finite for all the time instants. Next example is a sinusoidal signal, right? So we know what is a sinusoidal signal. The signal varies between some magnitudes plus minus a. If I say the magnitude is a, the magnitude of the signal keeps on varying in between plus minus some finite limits, and hence this signal also becomes a bounded signal because we are very sure that this signal will never go to infinity. Even if time tends to infinity, this signal will never tend to infinity, and therefore this signal is also an example of a bounded signal. Then what are unbounded signals? Unbounded signals are one whose magnitude tend to infinity as time tends to infinity. So the best example is a ramp signal. So we know that the ramp signal has a magnitude which goes to infinity. The magnitude goes on increasing and definitely it tends to infinity as time goes on increasing. As time increases, the magnitude tends to infinity. And therefore you call this signal as unbounded signal because here the magnitude is not finite. The magnitude is not finite. If the magnitude is not finite, you call the signal to be unbounded signals. Other example is the exponential signal. The exponential signal which is increasing with respect to time, e raised to t. Right, so e raised to t is a signal which is exponentially increasing with respect to time t, and therefore this signal becomes unbounded signal because its magnitude is not finite. If this would have been e raised to minus t, then with respect to the positive scale of the signal, this would have been exponentially decreasing signal. So if we consider only the positive scale of the time, then this signal would be called as a bounded signal. But here with e raised to plus t, as you see the signal is increasing with respect to time, exponentially increasing with respect to time, and hence this signal becomes unbounded signals. So clearly bounded signals are one which have finite magnitude and unbounded signals are one whose magnitude tend to infinity. With this understanding of bounded input, we try to once again revise the definition of stable systems. So stable system is one in which for every bounded input, output should be bounded. So if you give a bounded input to the system, output should generate a bounded output, right? So if you give a bounded input which is finite in magnitude, and if for such an input your system generates a bounded output, you will call it as a stable system. And since you check the stability with respect to bounded input, bounded output, you call the stability as also bounded input, bounded output stability, abbreviated as BIBO. So you also call it as a BIBO stability, bounded input, bounded output stability. So let us see how to identify whether the systems are stable or unstable with certain examples. So here is a first example. Determine whether the following systems are stable or unstable. So the example is yt is equal to t into xt. So this is the given system, and we have been told to identify whether this system is stable or unstable. So let us, how to test this system? So to test the system, we need to apply a bounded input. To test whether this system is stable or unstable, we need to apply a bounded input. So we'll assume that let the input xt be some bounded input. So the best example could be a unit step signal. With this, we'll assume that we'll apply a bounded input to the system. So we'll replace the input with a bounded input, which is ut. We'll assume that we have applied a bounded input. To test the system output, right, we need to go for BIBO. So BIBO says bounded input. First you apply a bounded input to the system, and that's what we are doing here in step number 1. We are applying a bounded input. Now what step number 2 says? It should give you, if you apply BO, you should get BO. BI, if you apply BI, you should get BO. If you apply bounded input, your output should be BO. That is, it should be bounded output. So now we have applied a bounded input. So whether this bounded input is generating a bounded output is what we need to test. So for this, we'll plot the output signal. So your yt now becomes t into ut because your input is a bounded input unit step signal. So we have replaced xt as ut. So yt is now t into ut. Let us try to plot this particular signal. So we know ut is a standard unit step signal having magnitude 1 for all the time instants from 0 to infinity. If you multiply this signal with t, the resultant signal is a ramp signal. At 0, right? At 0, when t is 0, magnitude becomes 0. When t is 1, magnitude becomes 1. When t is 2, magnitude becomes 2 because unit step signal has a magnitude 1. This is 1 throughout. So whatever is the magnitude of t is the magnitude of yt signal. So when t is 4, output is 4. When t is 5, output is 5. When t is 7, output is 7. So clearly understand that it is a ramp signal. And we know ramp signal, as t tends to infinity, the magnitude of the signal also tends to infinity. So when we applied a bounded input to the system, the system generated a unbounded output. The output of the system is not bounded. As the magnitude of the output is going to infinity, the output is not bounded. And hence what you can conclude? That as bounded input generated unbounded output, right, your system is unstable. So the given system yt, t into xt is unbounded signal. Let us move to next example. Yn is equal to x of n square. So this is a dt signal now. So to check whether this system is a stable system or an unstable system, we need to go for BI first. That is, we need to apply bounded input first. So we'll say let us apply a bounded input to the system. So we'll again take the example of un un is a unit step signal which is a bounded signal. So let us apply un as the input to the system. So it is as if we are testing the system with bounded input. So what is your un? Un, a discrete time signal, is samples all having magnitude 1, and the magnitude remains, all these samples have a magnitude 1 up to infinity. So magnitude of the signals is always 1, it is always bounded. The dot 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 indicates here that the samples are tending to infinity. So xn is a unit step signal. We have applied a bounded input to the system. Let us check the output of the system. So output now becomes a function of unit step signal. So yn is equal to u of n square. Yn is now u of n square. So let us try to plot these for various values of input time instants. So let us start with n is equal to 0. So y of 0 becomes u of 0. What is the value of u of 0? Is 1. When n is 1, y of 1 becomes u of 1. 1 square is 1. So u of 1, what is the magnitude of u of 1? Is 1. When n is 2, y of 2 becomes u of 4. 2 square becomes 4. What is the magnitude of u of 4? What is the meaning of u of 4? U of 4 means I am talking the sample at time instant 4. So at time instant 4, again the sample has magnitude 1. So we understand for any time instant, all the output signals are having magnitude 1. For any time instant you check the system is always giving you an output whose magnitude is 1. So if I try to plot yn will have all the samples with magnitude 1. So this is again a bounded output. So bounded input generated a bounded output. So you could see when we applied a bounded input to the system generated a bounded output, and hence we call the system to be stable. Here the given system is stable because it satisfied the BIBO stability. It satisfied bounded input generating a bounded output, and therefore you call the given system to be stable. Let us understand an example where yt is e raised to 4t u of t minus 3. Yt is e raised to 4t u of t minus 3. So if you study the system is already having a bounded input u of t minus 3. So input is already a bounded input u of t minus 3. So let us sketch the output of the system to analyze whether the output is bounded. So let us stepwise sketch the output signal. Let us start with u of t minus 3. So u of t minus 3 is shifted unit step signal. So we have drawn a shifted unit step signal, shifted by 3 units, delayed unit step signal. The magnitude of the signal is 1. Now we'll sketch this part of the signal, e raised to 4t. So e raised to 4t is exponentially increasing signal. So we could see here e raised to 4t is having a sketch wherein the value of the magnitude of the signal is exponentially increasing with respect to time. But the system is a product of these two signals. The system is system is e raised to 4t into u of t minus 3. So let us take the product of these two signals. So when we take the product of these two signals, signal starts at 3. As this magnitude is 1, the entire output signal magnitude is governed by the exponential signal, and hence if we see the signal starts at 3 and then from there on the signal exponentially increases with respect to time. And hence when we observe the output signal, we clearly understand that the output is tending to infinity. The magnitude of the output is tending to infinity, and therefore it is an unbounded signal. So what we observed? Bounded input resulted in unbounded output. Therefore the given system is unstable. The given system is unstable. Let us look at one more example where yt is e raised to minus 2t sine of 2t into ut. So this is the given signal. So as there is already a bounded input present, we'll analyze the output by directly sketching the YT signal, the system output. Let us directly sketch the system output YT. To do this, we will plot each of these signals independently. Let us start with e raised to minus 2t. So e raised to minus 2t is exponentially decreasing signal. Right? It tends to infinity on the negative time scale. On the positive time scale, it is exponentially decreasing. So this is e raised to minus 2t. This e raised to minus 2t is multiplied by ut signal. So ut is a unit step signal having a magnitude 1 existing from 0 to infinity. So when you take the product of these two, definitely it makes the signal a right-handed signal. There is one more term, sine of 2t. So sine of 2t is a sinusoidal signal, the sketch of which is shown here. So the resultant yt signal is a product of all the three. The resultant YT signal is product of all these three signals. So we need to take the product of e raised to minus 2t, sine of 2t and u of t. So let us take the product of all the three. So when we multiply all the three signals, the very first thing that's going to happen is ut will make the signals right-handed. So the entire signal is a right-handed signal. As this magnitude is decreasing with respect to time, it is going to modify the sinusoidal signal, and hence the sinusoidal signal is a damped signal. The product of all these three signals is resulting into a sinusoidal signal which is getting under damped with respect to time. Right? And that's why as the time tends to infinity, we observe that the magnitude of the signal becomes finite. Right? Remains finite. Definitely tends to 0. Somewhere it tends to 0. So magnitude is finite for all the time instants. Magnitude is not tending to infinity. The magnitude is decreasing with respect to time. So magnitude is finite. Right? Yt, when we sketch Yt, we observe that for all the time instants, the magnitude of the signal is always finite. And hence we say that output is bounded signal. Therefore, the given system is stable. The given system is stable.